Good morning, and welcome to the second of two videos on Chapter 5 in your textbook. At the end of the first video, we were on this slide, which was talking about the standard deviation and the range. And what you should know is that for any roughly normal distribution, the standard deviation should be equal to about 1/6 of the range. So what that means is that if you take a normal curve, all right, it's an ugly normal curve, but let's just pretend, where this represents the value of the mean, that you should be able to divide it into 6 equal portions, 3 on the left, whoops, that should be a vertical line, and 3 on the right, one more, and one more. Okay, and so we've got 6 equal sections, 1/6 here, 1/6 here, 1/6 here. So there's half on the left side of the mean, and then 1/6, 1/6, and 1/6 on the right side of the mean. Okay, and so that will in these portions, in other words, 3 standard deviations on either side of the mean, you're going to be able to fit about 99% of all of the data in this normal distribution. So what does that mean for us mathematically? Well, it turns out that there are some very predictable numbers that we can use with the normal distribution and standard deviation. You can see in this particular graph that we've got the mean located right here in the middle. And notice that this distance here represents 1 standard deviation to the right of the mean. That's what the positive sign here is. And this represents 1 standard deviation to the left of the mean. You'll see that this is approximately 34% of the data on the left and 34% on the right. So a grand total of 68% of the data in a normal distribution falls within 1 standard deviation of the mean. And this is great because it can be used to predict an awful lot about a population. All right. So again, 68% should be able to be found within 1 standard deviation of the mean value. All right. It turns out, and I wish that this picture had shown 2 and 3 standard deviations, but the 16% that you see over here is divided into about 11% and 5%. But we'll get to that a little bit later on. All right. But within 1 standard deviation of the mean, you find about 68% of the data, 34% below the mean and 34% above the mean. So if we look at a couple of different examples, what does this actually mean? All right, well, again, approximately 68% of the scores in a normal distribution are between the scores that are 1 standard deviation above and below the mean. And so if you look at the 3 distributions that are shown in this slide, in the first one, we have a standard deviation value of 4, all right, right here, okay? And what that means is that if the mean value is 50 that you see here, then 1 standard deviation below the mean, 1 standard deviation below the mean is 41, and 1 standard deviation above the mean is 54. And so what that means is that 68% of the data falls between 41 and 54 in terms of their scores. Now, if the standard deviation is larger, and we have a value, for example, of 7, for the love of God, what that means is that the scores will range between 40 43 and 57. I messed up on the first one. All right, it's not 41 here, it's actually 46. Sorry about that. All right, so here the standard deviation is 4, and so 4 below 50 is 46, and 4 above 50 is 54. So the 68% of the data falls between 46 and 54. Over here, with a standard deviation of 7, one standard deviation below the mean is 43, and one standard deviation above the mean is 57. And so therefore, 68% of the scores in this distribution fall between 43 and 57. Finally, over here, with a standard deviation of 12, that means that the scores here, one standard deviation below the mean is 38, one standard deviation above the mean is 62. And so that means that 68% of the scores in this distribution fall between 38 and 62. Okay. Now, if you take your data set and you add or subtract a constant number, so the standard deviation plus 4, or the standard deviation minus 3, all right, that does not change the variability. All right, in other words, the entire curve simply moves up or down by whatever that standard deviation, or I'm sorry, but whatever that constant value is. All right. However, if you multiply or divide by a constant, that will change the variability, meaning that it'll take the curve and squish it or expand it. Okay, so adding or subtracting simply moves it from one place to another along the x-axis. Multiplying or dividing either expands it or squishes it. Okay, just to keep that in mind for future reference. Okay, now what we've talked about here in terms of variance and standard deviations are calculations regarding a sample of a population. Now, of course, in real research, what you're trying to do is use the sample to make inferences about the population as a whole. And so this is going to alter our calculations just a little bit. So right now, let's spend a few minutes here talking about what we call the population variance and the population standard deviation. The population variance is the true or actual variance of the population of scores. All right, and the formula here, rather than an s squared, we're going to use this Greek letter here, which is I don't remember what this letter is called, but this one is called mu, and this represents the actual mean of the population. So the formula itself is the same as the one that we used last time. The only difference is that it's now we're using mu instead of x bar. We're not talking about the sample mean. We're talking about the population mean. So this is the population variance. It's the true or actual variance of the population of scores. All right, and notice that it takes each individual score, subtracts the population mean from it, squares that term, and then sums all of them for in other words, for every single data set or data point. And then it divides by n, which is the number of data points in that given population. Okay, so this is the population variance. Now, to calculate the population standard deviation, what do? Well, if you recall, the sample variance, to calculate the sample population, let me start that sentence again. To calculate the sample standard deviation, you simply took the square root of the sample variance. Well, guess what? You do exactly the same thing to calculate the population standard deviation. You simply take the population variance and take its square root. and that gives you the population standard deviation. So the population standard deviation is the true or actual standard deviation of the population of scores. And notice that all I've done here is I've taken the formula from the previous page and taken the square root of both sides. All right, notice there's no little squared number here, and I've got the square root of the term on the right-hand side. All right, so calculating the population variance and standard deviation is the same as calculating the sample variance and population. The only difference is that we're using the population mean instead of the sample mean here. Okay, that's the only difference. Now, unfortunately, calculating the actual population variance and population standard deviation is a near impossibility, because it's almost impossible to go through an entire population and measure every single member of that population. And so, in reality, rather than use the formulas that we just talked about, we have to use what we call the estimated population variance and the estimated population standard deviation. And so what that's going to do is it's going to alter our calculation just a little bit. Okay, so let's look at this. All right, why do we do this? Well, first of all, the sample variance, which notice is a capital S squared, is a biased estimator of the population variance. All right, meaning that it's not quite correct. And the sample standard deviation is a biased estimator of the population standard deviation. All right. And the reason that they're biased is that they tend to underestimate the true population parameters. In other words, they tend to underestimate just how large the spread of the data is. And so, in order to figure out a better way to do this, we have to use a different calculation. So we don't want to use this biased sample variance and this the biased sample standard deviation. In order to do this, what we do is divide the numerator of the sample variance by n minus 1 instead of n. And what this does is it gives us an unbiased estimator of the population variance. So look at the formula here. This is the same as the formula that we used in the last case when we calculated the the sample variance. I have a ghost in the machine. When we calculated the sample variance, all right, we divided by n, but now we're going to divide by n minus 1. All right. What this does is it removes the bias from our estimate. The same thing is true for calculating the estimated population standard deviation. All right, by dividing the numerator of the sample standard deviation by n minus 1, we have an unbiased estimator of the population standard deviation. The formula, again, is the same as the formula for the standard deviation, except that we're going to divide by n minus 1 instead of n. All right, this again removes some of the bias in our estimation. Now, what is this n minus 1 thing? All right, the quantity n minus 1 is called the degrees of freedom. And this is simply the number of scores in a sample that are free to reflect the variability of the population. And it's symbolized by df. Okay. Now, if you had a number like 8 minus x minus y, all right, I can choose any number that I want to for x, and then that limits the number of y values that I have. Okay. So if I said x is, I'm sorry, let's say make this equal to 2. So let's say I make x equal to 3. Now, what does y have to equal now? All right, I'm limited now in my choice of what I can do for y. Well, 8 minus 3 is 5, so y must equal 3 as well. Okay, 8 minus 3 is 2. Now, what that means is that I'm limited in my choices, and the n minus 1 reduces the choices that I actually have. Now, keeping the symbols all straight, okay? Capital S squared and capital S describe the variability of a sample, okay? Little s squared estimates the population variance, Sx, and Sx estimates the population standard deviation, okay? So big S describes the sample. Little s is an estimate of the population. And these two calculations use n minus 1, which is the method of calculating the degrees of freedom here. All right. So these are the numbers that really become important. If I want to describe the sample, I use capital S. If I want to describe the population, I use lowercase s. All right. And the lowercase s numbers are simply estimates of the population variance and the population standard deviation. All right. So what do we do? How do we figure all of this out? Well, let's have a look at an organizational chart of descriptive and inferential measures of variability. Okay. If you are just looking at a sample here, okay, then the formulas that you're going to use will simply use the number of data points in that sample in order to calculate variances and standard deviations. To describe the sample variance, you simply compute capital S squared, and taking the square root gives me capital S. To describe the population variance, all right, if I actually do measure all of the members of a population, I use this symbol squared, and taking the square root to give me the sample of the standard deviation, I use this. Now, in both of these cases, I'm talking about describing something. All right. So here I describe the sample, and in this column I'm describing the sample, and in this column I'm describing the population. It's very difficult to write with a mouse. Okay. However, more often than not, in real research, I need to make inferences. In other words, I need to use the sample in order to make inferences about the population. And so in this case, I need to use the degrees of freedom. So inferential measures are used to estimate the population based on a sample. And here, again, the formulas use n minus 1. To estimate the population variance, I use little s squared. And to estimate the population standard deviation, I use little s. All right. Now, we're going to pretty much ignore the middle two here. All right. We're going to either describe the sample or use the sample to estimate the population. Okay. Those are really the two things we'll concentrate on. And so let's look at the formulas that we have now. And these are written slightly differently than you've seen before. In order to estimate the sample variance, we use capital S squared equals the sum of x squared minus the sum of x quantity squared divided by n, all divided by n. So this is the formula for sample variance. All right, sample variance. Now, of course, in order to calculate the sample standard deviation, all I have to do is calculate the square root of both sides of this. All right, but again, notice that this formula is written a little bit differently than we've presented it in the past. All right, but the key here is that we're dealing with the value n instead of n minus 1. If we take the square root of both sides in this case, then again we get capital S for standard deviation equals the square root of the sum of x squared minus the sum of x quantity squared divided by n, all divided by n. Okay, and so that'll give me the sample standard deviation. And again, this formula is a little bit different than you've seen in the past. Now, if I want to estimate the population variance, then I use this formula. And notice, this is very similar to the one I saw before, but now instead of n in the denominator, I'm using n minus 1 for degrees of freedom. And notice again that here, oh, God's sakes, I'm using little s. All right, and so little s squared, in other words, the population variance, is equal to the sum of x squared minus the sum of x squared, quantity squared, divided by n, all over n minus 1. Okay, that's the estimated population variance. Now, to calculate the estimated population standard deviation, I use this formula, which is exactly the same as the one on the previous page, except that I've taken the square root of both sides. So little s equals the square root of the quantity x squared minus the quantity x squared all over n minus 1. All right, and so that's the estimated population standard deviation. All right, and I think, yeah, we'll end it there for this video. Stay tuned for video number 3 for chapter 5, and I hope you learned something.